So I'd like to welcome two guests to come to the stage to speak for a particular session that's entitled Simulating for Uncertain Certainty. Just kind of looking back at my own career in architecture, back in about 2003, I joined a firm called Grimshaw Architects who've built quite a lot of works throughout the city of London. I was working for their New York studio, and it was about 2004. I'd only been there for about a year, was well versed in the history of the work that they had done. When I saw a presentation by the Bentley research team at the Center for Architecture, it was my first chance of ever seeing generative components in action. They showed off a project that was an early Grimshaw project, a perfect example of the complexity that you have to deal with in changing site conditions, structural analysis, all sorts of work. It was the Waterloo International Terminal. Little did I know that the three founding directors of that group had actually worked on the original team for YRM to put together the earliest parametric models. So from a personal perspective, this was an amazing experience for me. My entire career in computational design, my association with the Smartgeometry group began with seeing that work, and it's continued for, I guess for me, getting close to a decade now of working with them. So I would like to thank the team from Bentley to come to the stage and give us a presentation. Thank you very much. Come on up.
Great. Well, thank you, Shane, and thanks, folks, for your attention. I know lunch is next, so we're cognizant of that. I guess what we wanted to do is share a couple of viewpoints, and you know, why does a software company care about this, and why do we invest in this, and how does it relate to our experience? My responsibility at Bentley, I'm the Vice President of Core Marketing, and I look at all of the things that Bentley makes that span all of the markets that we serve, and including the building market. And our mission as a software company is to provide software and services for all types of infrastructure with the goal of sustaining society. And we have it sounds like a high-minded mission, but we very much take it to heart. And we have software and services for all different types of built infrastructure. And one of the values that gives us is the ability to take the lessons from different industries and cross-pollinate and fertilize the advances in one area and apply it to others. We have software, I think it's 250 different software titles that are actively applied on all different types of structures and systems. And we're a private company, so we have the ability to make our decisions and set our strategy ourselves without having to respond to stakeholders and the stock market. So I'm going to borrow from our annual report. I'm not going to give you a corporate update, but I do want to highlight a couple points that are relevant to you, if you will, as our stakeholders. So we're a strong company, we're a growing company, we're a global company. We are, our dominance and our strength is at the top end of the market, so the top design firms by all the ranking systems, the top construction and engineering and architecture firms around the world. And we address their needs through sort of three principles. We think about information modeling as the design and simulation of things for the purpose more of understanding them before you make them or realize them. And we purposefully say information modeling as opposed to, for example, building information modeling, because that has a very specific limiting connotation. And that information model is about performance, and it's about sequence and process, not just about a static representation of the end product. We also look at it from the concept of integrated projects and recognizing the trends in the industry of bringing expertise from construction into early design and fabrication to simulation and closing that loop and integrating the process and supporting collaboration while doing so. And then lastly, focusing on the result, having the infrastructure be intelligent, take all that information from the design, simulation, construction, and delivery phases and have it persist through the operations of the asset. And in fact, half of our customers are owner-operators who are operating transit systems, buildings, airports, factories, and so forth through their life cycle and using this information in that mode. The other important driving concept for us is the concept of information mobility. And by mobility, I don't just mean mobile devices. I mean the concept of letting the information move from person to person and system to system and process to process. And we have a lot of technologies and software and services to support that with our own software and with all of the common software at play in the AEC market. We're also focused on innovating. We typically are spending 20% or so of our investment or of our revenues, reinvesting that in research and development and acquisitions. And I think last year we invested over $100 million in that, and since 2005 it's over $1 billion. So we take it very seriously of looking for that innovation and applying it back into the technology that we offer the market. So I want to focus on a couple innovations that we highlighted in this year's annual report. The first one is the iModel technology, and it's a recognition that there are a host of industry standards for information exchange, none of which actually fully get the job done. And so we have a technology called iModels that allows the integration of information across systems, allows you to get to that information from database systems and spreadsheets and so forth without needing any of the originating authoring tools. And that's taking off like crazy for obvious reasons. The other one is recognition that this information is tied to the real world. And real buildings have real sensors that are bringing in data about their performance and their health and operational status. So asset health monitoring with our Avara software and so forth is looking at the operations of the building, doing predictive maintenance to repair and replace things right before they fail instead of after they fail, and optimize the performance of the engineering systems in buildings. Tying that information into historical data and into benchmarking data and into predictive algorithms that relate multiple systems against each other so that you can have that health planning for your building based on what the building is really doing in similar buildings of that type or in that region. Another data type that's really emerging strongly is point clouds, and we saw Kinects and other systems here in a lab environment, if you will. Well, they're in the real world too, and with partnerships with companies like Trimble and so forth, that you have LiDAR data, point cloud data. We have technologies that manage multiple sets of point clouds over time and progressive analysis of point clouds, doing clash differencing between point clouds, tying the point clouds into your information model so you can link points to data that's in a design or simulation analysis model. Tying those into streaming services, so all of our desktop applications and web services allow you to stream from multiple terabytes of point cloud data just the points relevant to what you're looking at or the area of the model you're interacting with, so you can do it in real time and you can interact with that data and actually do day-to-day construction progression point cloud scans of your site, for example. And then the last one is actually going in the other direction, going from the virtual world back to the physical world with lasers and using laser positioning and layout tools. So taking your digital model, driving through GPS, the bulldozer leveling the site, but also using laser positioning to lay out where materials get installed or hung on a structure or attached to another material on site in the building. And then the last one is taking that mobile, allowing all of those activities and the interaction with that information to happen through your iPad, through your phone, wherever you are. Allow that information to be delivered to those devices and work in an offline mode. We actually had an interesting, I think it was even the Crossrail project here in London, where they don't want the workers connecting and interacting with live data while they're standing on the steel beam or out in the construction site. So you have safe zones where you go online, take down the information, go out and use a cached version on site or use the live information. And understanding the workflows of a mobile worker is a whole new paradigm in this industry, and you have to connect back to services for it because you need the processing of the cloud-based computer services to do that. So the other thing is we have a whole applied research group, and we look at the research with applied being the key word. How do we bring this into products and services that actually affect problems and objectives that the design and construction and operations industries care about. And maybe Generative Components is the grandfather of this group and one of the first research projects, and is still active as one of the platforms for that research. But we're now bringing in genetic algorithms and bringing in optimization systems and bringing in predictive systems to tie and build off of those technologies with all of our software as an engine for it. And the other one is augmented reality, looking at, for example, here an example of seeing what's underneath the street, tying your model with your GIS systems and GPS location to see utilities and systems before you excavate. Or looking at your building model and being able to peel away the skin or see the virtual wall section of the building that you're standing in front of. Or using construction as-built information and seeing the conduits and pipes inside a wall before you do some maintenance on that wall through your iPhone or through your, I guess soon, Google Glass. So those technologies are not just research, but they are being applied into our offerings. Now, so every year we have a competition, or we allow our users to have a competition, and they submit projects that they find inspiring. And it's the Be Inspired Awards, and it's at our Year in Infrastructure Conference. We'll have it again this year, coincidentally, here in London. So before coming, I was looking at those projects and relating them to the theme of the challenge and to coming to London. And one of the categories, there's 13 categories, but one is innovation in building. And last year's finalists were great projects from around the world. Morphosis with a project in China, Arthur Golding Associates with a great library competition project in Helsinki, and the winner was here in London. So King's Cross Station, just down the road, fantastic project. Go check it out with a big Generative Components truss in the middle. And I thought, that's pretty cool. I should probably mention that. I wonder what else is there. And in the construction category, a fantastic project of looking at mobile and field worker processes with our software from HNTB for their construction work. Another great project with using EcoSim Building Designer for construction modeling of a project in Boston with an existing shell that needed to be maintained and tied into other systems. And once again, a winning project here in London. So with Taylor Woodrow and BAM Nuttall as a joint venture, looking at grout cores to support the tunneling for part of the Crossrail project near Victoria Station. And then generative design. So projects using generative components and other Bentley software. A great project in Abu Dhabi by Lab Architecture Studio. A great center in Atlanta by Stanley Beam & Sears. And once again, a winner here in London. So last year was the year of London for us with these awards, and it just worked out that way. Again, this is a fantastic project, and in fact, I'd like to thank the folks from Partington for giving us a presentation on that the other day for the press and some other folks. Just a few blocks from here, worth going out and looking. And I couldn't be in London and not mention one of the largest construction projects in the world, the Crossrail project, all being managed in Bentley software as well. So we, in our annual report, actually recognizing these things, looked at London. And the number of projects and firms and activities here that we're involved in is a great representative sample. And I'd encourage you to download it and take a look at those case studies ranging from the London Eye and the Shard and other projects to see how they work. So I then thought about the theme for this event and the concept of uncertainty and what does that mean from our perspective. And on the one hand, uncertainty is it provides opportunity. Because you don't know the answer, you can explore different directions and you can find the degrees of freedom that whatever your medium is offer you. And maybe you're Jackson Pollock and you're having fun making a mess in your living room. On the other hand, uncertainty is risk, and probably the biggest constant in the building industry is a recognition and response to risk. Maybe it's not the risk of not knowing that the world is not, in fact, flat, but it's safety, it's cost, it's sustainability. It's all of the issues that we as architects and engineers face in actually delivering real places that people will habitate and visit. So we as a set of professions tackle that uncertainty in real projects in practical ranges. not everything can be anything. There are reasonable expectations as to what the weather limit will be, what the loads on something will be, what the amount of movement or intended uses will be, and we operate and design and consider and simulate within those ranges. And then we simulate the performance of each of our scenarios and our projected solutions so that we can increase our certainty that the building, in this case, will best accommodate its potential set of futures. And we do that with the two objectives of managing and reducing that risk, that set of risks, and providing the design opportunities to deliver the buildings and opportunities for use of those buildings that are the objective of the project. So with that, I'm going to turn it over to Santanu, who will tell you about some of the actual technology that helps us achieve those objectives.
Thank you, Hugh. Good afternoon, everybody. My name is Santanu Das. When I first was given this title of Design of Certainty and Uncertainty, I thought it was a bad joke at first. I thought there might have been a mistake. But then I kind of thought about it for a little bit, and I thought, this is exactly what Bentley's simulation tool is actually set up to do. So let's look a little bit about how simulation can actually work in your benefit in the theme of sort of resilient structures is the way we like to position it. So we had a lot of disasters in the last couple of years, right? Things that were uncertain, things that you could have never really predicted, and in terms of the outcome of it, couldn't have predicted either. Here was the big explosion of the BP offshore oil rig in the Gulf of Mexico in the United States. 5 million gallons of oil was spilled, 53,000 gallons per day, but probably the most remarkable number is only 11 deaths that was there. Using some of our predictive analysis, what we call blast technology that we have in a lot of our software, we can actually, and we're asked to simulate the explosion of the jacket ring of this particular system underneath the water. So you can see here, using an advanced nonlinear finite element simulation, we can actually predict exactly when the joist would buckle under the water. And there's a lot of stuff that you have to think about. You have to think about the temperature of the water, the marine growth that's there, the impact of the blast, how the water uses sort of as a blanket to shield there. But using all of these mathematics and running this simulation on our cloud technology, we were able to actually figure out where the different weaknesses were due to this blast. And by the way, it really wouldn't have been any type of steel structure that could have been built to resist it, but things that could be done in the future to kind of help prevent the collapse in such a way that those 11 deaths probably could have been spared. Fukushima, I think everybody knows about this out in Japan a couple years ago, a big disaster there. We were asked to simulate the nuclear core reactor with a big steel structure on the top and a steel or a concrete encasing there at the bottom. What we found out after were that even though there was a 9.0 earthquake in there, it wasn't the earthquake that actually caused the damage that you had there. It was actually the tsunami and the water turning off the generator, thus the cooling mechanisms were off, and therefore things started to heat up, and the hydrogen and oxygen, the water boiled over, steamed over, and created hydrogen gas, which then exploded. But the steel structure actually stood up, there. And using, again, simulation technology that we have in the Bentley products there, we were actually be able to properly look at what that steel truss's behavior was in a 9.0 earthquake. Again, you never predict that you're going to have a 9.0 earthquake with a 33-foot tsunami, or you're going to have a giant explosion underneath the water that takes out an oil rig there. But these are things that now with technologies like this on the cloud, you can actually start to predict. The other thing is base isolation, right? So what can we do in looking at buildings or to prevent things like Fukushima going forward in here? This is kind of what happens on a shaker table that you saw there during a 9.0 earthquake in a building. But again, using new technology, something called base isolation, which are now being built in buildings all over the place called smart systems, you can actually reduce the effects of a 9.0 earthquake down to a 5.8. Right? And that's a lot. That actually is quite a bit if you look at its logarithmic, right, on a Richter scale there. That gives plenty of opportunity for people to egress and get out of their particular building systems in time and into safety. And again, these technologies were not readily available, not only from a construction point of view, whether you're looking at friction and pendulums or so forth, but also just from an analytical point of view, right? These used to take hundreds and hundreds of hours just to run one scenario. But now with the power of the cloud and how Bentley simulation services are worked up on there, it's very easy for you guys to kind of figure what would happen with these systems. And even things like wind farms. Offshore wind farms are pretty big, right? And if you look at here, what happens to this particular wind farm doesn't look very promising, right? And and this actually happens quite a bit, maybe more in America than anywhere else. We're a little bit lazy when we construct some of this stuff, but it actually happens quite a bit. And if that 8-degree angle of which that particular nacelle is supposed to run the blades on there, if that's off by just a half a degree, goes to 8.5 or 7.5, that's the results of what you're going to see over there, right? So there's a big push by 2030 to get 300 gigawatts of power out, in terms of solar or in terms of wind power there, right? Which means you have to build over 7,000 of these wind farms a year. Up to 2017 in order for this to happen. And the problem is that these things are very complicated in terms of the wind patterns and what happens when you have one wind farm connected to another wind farm, because there's a lot of airflow problems that are there. Again, this can be simulated. This all uncertainty stuff can be simulated using the simulation technologies that Bentley provides today. So, here's one last thing on resilient structures. This happened in Rio de Janeiro in 2012. I don't know how many of you are aware of this 20-story building that collapsed. Again, had some fatalities. But you notice here this little drop analysis, a simulation that was done again with Bentley software. Basically what happened is that this thing was under retrofit. It was a brownfield project that was going on. There was some stories whether the construction was illegal or not legal, but what had happened is that they were moving an HVAC equipment with a crane, and the HVAC equipment dropped off the crane, landed on that floor, right, which was what we call a drop analysis, caused that floor to collapse, and the rest, obviously was more like a domino effect there, right? But again, these different analysis or these high-end simulations can now be predictable, right? I mean, no one really thinks of dropping, mechanical equipment that weighs, 11, 12 tons from a crane at a height of, 40 or 50 feet onto a floor. And it's really hard to do those types of predictive analysis, but now can be done with our software. So at the end of the day, the point is that even as uncertain as some of these situations may sound, they actually do happen. They come to fruition, unfortunately, in life, right? Before, building codes never had, a simulation or a scenario of a plane hitting a building or a 9.0 earthquake happening that causes a 33-foot tsunami or other types of blast patterns. But they are becoming, unfortunately, very pervasive in our life. And you have to sort of build these analytics into your intelligent model, right? It's not just about the geometry and things like that, but the geometry has to be self-aware so it can derive itself into these analytical models. So when you have this physical model, you want to be able to do an acoustical analysis. You want to be able to do a heat analysis, a thermal analysis, or some kind of solar insulation analysis. And you don't want to have to remodel every single time. It should be smart enough to self-describe itself and prepare itself for that type of simulation, right? And that's what Hugh was referring to in our new iModels technology that Bentley has. By putting all of our sophisticated analyses on the cloud, we are giving access to really whatever publishing application you want to start with, Bentley or non-Bentley, right? We take that particular information through an iModel, we scrub it, and we say, okay, this is fit to do a drop analysis. This is fit to do a thermal analysis. Or, you know what, you're pretty close to doing an acoustic analysis. You just need to provide me this many more pieces of information, right? So making this type of predictive analysis very easy for you guys to use with your conceptual or detailed models that you have here. So what kind of answers would you get? Well, it kind of depends at what stage you're at, right? Not everybody has the ability to run those types of drop panel analysis or blast analysis or so forth in there. But if you wanted to get some basic rule of thumb in your conceptual stage, I think Shane had mentioned you got to make sure you put a big asterisk marks on some of these analyses. He's absolutely right. You can get a big red, yellow, green as to where am I with my egress, or where am I with my solar exposure, or where am I with my line of sight or my shadowing, there. And Bentley is smart enough to include these analytics at your fingertips, knowing that we're very agnostic in terms of what type of publishing model you come from there. So computational design to us is something that's kind of advanced, right? It's started off with maybe sketching and modeling and then some parametrics that you see in generative components and other types of systems, but we really believe the future is the built-in computational design. As the model is progressing it should be able to be self-aware and tell you how it's handling the different analytics that it's exposed to, right? It shouldn't be a serial process of let's build, and then analyze, and then modify, and then analyze again. It should be integrated, and it should be in real time. And with Bentley's cloud technologies, this is all now possible, right? So remember I told you before, the real situation or the real task is to have a good information model, right? And that's what we provide in Bentley systems, as well as other parametric systems there as well. And if you have a good information model, not only can you derive the analytics, but you can also go from down to design to construction as well, right? So this brings and shifts the entire life cycle to much earlier in the process, right? So if you look at this particular example here, this was a construction that was done of a hospital building or something like that over there. And it was done, using Bentley systems that we have, a combination of our Pro Structures and other Ecosim building designer. And you can see that the columns and the slabs and the footings were all being detailed out. Well, the fabricator knew that the analytics were going on simultaneously, so he said, well, that means that the model that I have in hand is always up to date, right? And that's the great thing that you get with the iModel technology. So he went and started doing his bar bending schedules, right? And this is what we call modular fabrication. Things can be fabricated, shipped out modularly, and then assembled together almost like an erector set. Right? And you'll see many of these projects happening in China, in Southeast Asia, and so forth on there, right? So in this particular example, the detailer ASA took that particular model, created all of its bar bending schedules, started putting out all of its rebar schedules in there, and you can see here, started printing out the rebar tags in real time, right? As the model was actually being finalized and developed. Now the great thing about it is that as this thing is being erected in the field, you can use our mobility, just like Hugh was talking about with our iModels, take this particular model, and you can kind of look and observe and see if the construction is as planned in the work intent model, right? So here we can actually take those laser tags, scan them, and it will actually point to where those rebars are in the iPad model, right? So you know which particular systems have been shipped, which particular systems have been set in place, have they been set in place in the right place or not? Again, all integrated through this system that we have. So how do you actually make the analytics shorter, right? How do you get the feedback so the constructor and everybody can get to work a lot faster, right? I think everybody knows in the serial process, which I talked about, which is model, analyze, you don't get to go through too many iterations, right? Some studies that were done at Stanford and other places show that your average number of iterations, maybe 2.5 iterations per your model life cycle that you have in there. So the thing that you got to really do is you got to shift everything to the cloud. And I think everybody understands that, right? But really what you need to do is not only integrate the power of the cloud with advanced analytics like I was showing, but you got to make the analytics talk to each other, right? And that's really, really important, right? What we call multidisciplinary optimization, right? The output of structural should influence the input of energy. The output of energy should influence the input of acoustics, right? Everything has to have some relation. You can't work in silos anymore, right? Because then again, it's serial and you can't really investigate how each one affects each other. So if you look at this particular example here, this was the bracing pattern on that same hospital that we were showing there. And there's a lot of different things a structural engineer has to look at. He has to say, well, how do I optimize this bracing frame so I can have the lowest amount of period, in terms of a structural vibration that may occur in terms of an earthquake. And there's a lot of different patterns that are available, right? These are the constructible patterns, right? This is his constraints. He knows that he can't do some funny shape or whatever, or maybe you can. I've seen a lot of your guys' models. It looks like you can do any funny shape out there. But practicality-wise, this is what the contractor can do, given the shipping and the materials and the timeline that he has. Well, I don't have time to create all of these models and test all of these models, right? So usually you over-design. But what we can do now with our new genetic algorithms and our optimization framework that's built in with generative components and our cloud-based analytics is that we can do all of this scenario management for you, right? So what you can happen here is that you'll notice that we find out that this particular frame is best suited using our algorithms and stuff to have a frame design like this. This is going to be the lowest amount of period based on the constraints that the contractor can provide, because it can't just be any material, because he may not have access to them, so it increases the cost. Given all that as an input, our particular framework goes through and tells you that this is the bracing pattern that you would need. So let's kind of take a look at how that would work in a real example of a bigger building. Here you have a hospital with a bracing frame system, right? Very similar to the other one that we had. And it could be knee bracing, it could be an X bracing, it could be channel sections, HSX sections, angle sections, or so forth, right? There's a lot of variations, right? Each of the bracing configurations also has another axis of the cross-sectional type, that you have. This is all available to the contractor. He doesn't know what the optimal configuration is. The structural engineer doesn't have time to go through all of them. Even just looking at this configuration here is probably on the order of 32 or 34 combinations, right, that he has. He doesn't have time to build it. So what we do is using Bentley's scenario management with our generative components is that we can optimize and automatically generate those models for you by you giving the constraints of what kind of patterns that you want. All of those models are created and uploaded onto our cloud. And you can see we design them in real time and we compare them against many different scenarios. You can look at the overall utilization ratio if you're a structural engineer. You could look at it by material type to see what is most weight that's given there. You can look at it as story drift to see which one causes the most story drift here. You can also look at it by cost. You'll see those black lines in there are kind of looking at what the cost is of your particular option that you've picked in there. So automatically these 60 options were created for you, analyzed for you on the cloud, and given to you to compare in a very, very easy manner. And that's really where we believe the connection of, designing for uncertainty and certainty kind of crosses, because you just don't know at the end of the day, and you don't have time to go through 1,000 scenarios. So if we can cull that down for you to something that's much more manageable, it gives you a lot more options to investigate rather than wasting your time of making these models, right? So at the end of the day, we partnered with Microsoft to say, we really need a large system for us to make this happen, right? A typical offshore simulation of the nuclear blast on the pole can take about 14 to 15 hours to run on a very, very high end computer, right? And that's because of the fatigue analysis that you have to do. So imagine you can't run 50 of those things. You just don't have time. So we were working with Microsoft and their Azure platform over there, and we are writing code right next to them to make sure that our simulation technologies works really well with their particular system. And this is going to be launched for the public sometime at the end of this year. So if you guys are interested, let us know. You guys can play around with it. So that kind of ends my presentation on designing for certainty and or certainty in kind of the realms of uncertainty. And again, I want to thank you guys for your time. I know we're standing between you and lunch, but again, Bentley's very excited to have you guys here, and good luck with the rest of your conference. Thank you.